In more complicated circuits, we need to use other methods. Now, one of the methods that we use in some circuits, and it's not the unique one, but one of the commonly used methods in dealing with circuits is what we call Kirchhoffs rules. There are two rules. One of them, we call it Kirchhoffs voltage or loop rule. Okay, some people just designate it as KVR, Kirchhoff's voltage rule. That one is a consequence of the conservation of energy, and it essentially says the sum of voltage drops around a loop in a circuit is zero. The sum of voltage drops around a loop in a circuit is zero. It essentially says if you go around in a loop, if you go back to the same point that you started from, you are going to go back to the same electrical potential level. That's essentially what it says. Now, the second rule is what we call Kirchhoff's current rule, or KCR. That one is in consequence of the conservation of charge, which says in any point of the circuit, the current going into that point is equal to the current coming out of that point, which is, in other words, current entering is equal to current leaving. If you think of it in terms of junctions, places where the circuit break into different paths, then you look at the different currents. For example, I have here I1 coming in towards that junction, but I2 and I3 in this case are coming out of that junction. So what the Kirchhoff's current rule says, the sum of the incoming currents, which is in this case only I1, is equal to the sum of the outgoing currents, or the leaving currents, which is in this case I2 and I3. I1 is equal to I2 and I3. Okay. This is the rules. So how do we apply them? This is what we do. First, we label all currents. You notice here the circuit, I purposely put it there without any currents. And notice we have more than one power source, E1, E2, and E3. We have several of them. Now, to label all currents, look what it says. Choose any direction. This is important. In a circuit like the circuit that we have right now, most often we cannot predict correctly the direction of flow of the current. Most often it's something that we don't have the intuition to figure out immediately. So what we do is we choose them randomly. Okay, let me do that. What does that mean? When we look at this circuit, how many different currents we can have? I'm going to use color to illustrate that. So if I start here, I have a branch. But the minute I come here, it branches in two. So I'm going to have a unique current in whatever I marked in yellow. Okay, I'm going to remove now the marking. Okay, just go back to black and mark that current. Let's call it I1. Okay, I'm going to mark it flowing this way. And the direction I marked it is random. So I marked it flowing that way. I could have marked it opposite way. Now notice I could have labeled it in the bottom as long as I stick to the same direction of flow. Now remember we said the minute we reach this point, that current is not going to be the same anymore in whatever is going to follow. Let's go back to the yellow color and find a place where I have another unique current. For example, here. That's one branch. There is no branching between the top point where I started and the bottom point, so I should have the same current there. Now that current, okay, I'm going to erase again the marking. I'm going to call it I2. Now how am I going to label it? Let me choose it up. Again, remember I'm doing that randomly. Now the next thing, going back to my yellow color, so when I start here, I have some branching. But the branching connects back in the bottom here. So whatever I have in yellow here, that's a one wire that should have the same current. I'm going to keep the yellow there. I'm not going to remove it this time. That current let me call it I3, and I'm going to randomly choose it oriented like that. So this is I3. Okay. Remember, that's just a one loop. That loop is broken. Sorry, here. Let's use another color. Is broken into two paths here. The green one, let's say the purplish one. Those are going to be two different currents. Let's call the green one I5, and I'm going to label it like this. And the purplish one, let's call it I4. And choose it like that. Okay? This is the labeling of all currents. I did that. The next step is to label plus and minus for all elements in the circuit. Now, to put just in the graph, to go around, put a plus and a minus. For batteries, it's easy. The negative lead is a minus, the positive lead is a plus. For resistors, we should use this rule. The current goes in from the plus and exits for the negative. Current goes in from the plus and exits at the negative. Okay, let's use the red color to do that. Okay, so batteries, minus, plus, minus, plus, minus, plus. Now for resistors, we check the currents that we have already assigned. Now, for example, for R1, the current flowing through R1 is I1. I1 is entering from this side and exiting from this side. So this side where it is entering, we label it as plus. This side where it is exiting, we label it as a minus. Same thing, let's check out R2. The current is going from the bottom, so this side is plus, this side is minus. Let's look at R5. Current is coming in from the right, so the right side is plus, the left side is minus. For R3, the current is coming down from the top, so the top is plus, the bottom is minus. Same thing for R4, top is plus, bottom is minus. That's the way we should label them. Actually, probably it makes sense to have step 4 before step 3. Or actually a different version of step 4. Let's make it step 2I or 1 or whatever. So we are going to write the voltage drop for each of the elements that we marked. Now for E1, that's easy. It is just E1. It is already written. It should be given. For E2, same thing. For E3, same thing. Now for resistors, we use Ohm's law. For example, for R1, Ohm's law is going to be R1 times the current flowing through R1. The current in that loop is I1, so for R1 is going to be R1 I1. For R2, the current through R2 is I2, so writing Ohm's law for R2 is going to be R2 I2. For R5, the current flowing through R5 is I3. So for R5, it's going to be R5 I3. For R3, I'm going to write it way down here. It's going to be R3 times I5, the current flowing through R3. And for R4, it's going to be Ohm's law again, R4, and the current flowing through R4 is I4, so it's going to be R4 I4. Now, step 3, 4, and 5 are going to be what actually is going to get us to finalize the setup. So what I did here is the setup, but the actual calculations are going to come next. So I'm going to do that in the following screens. As I work the problem. Now, I'm going to do that in the following screens. I'm going to do that in the following screens as I work the problem. You notice in a little while ago I kind of took care of everything. But really, if I'm trying to work the problem and if there is a way to simplify it, I should do that. And in this particular circuit, there are a few simplifications I can make. You notice here that actually, let's see, in color red, R3 and R4 are in parallel, so the first thing I need to do, I need to replace them by their equivalent. That's R34. I can find it by writing 1 over R3 plus 1 over R4. Okay, so I can find R34 and then simplify it. And then once I do that, my circuit is going to change into this. R1, R2, this is E1, E2, and then I have E3, and then I have R23, R34. This here is a little long, and then I have R5. Now we notice that R5 and R34 are in series, they're in the same branch, so we can combine them. As we combine them, what we get is R534, which is equal to R5 plus R34. So my simplified circuit is going to be E1, R1, R2, E2, E3, and R534. That's my simplified circuit, the circuit I'm going to work on from now on. So this is what I have. So I'm going to go back through the process that I did a little while ago, label all the currents like I did before. So this is my I1, this is my I2, this is my I3. And then the pluses and minuses like we did before. Plus here, minus here, minus here, plus here, minus here, plus here, minus here, plus here, plus here, minus here. And actually I think I chose I2 a different direction, so let me go back to make sure to stick to, to stick what I did. I had I2 going up, so I'm going to change that. So I2, I'm going to fix it. I'm going to have it go up. So now the labels then for R2 are going to be plus here, minus here, and I3 is that way, so this my label plus and minus. The next thing is the voltage drops across each resistor, so that's going to be R1 I1. This one is going to be R2 I2, and this one is going to be R534 times I3. So we are set. Okay. Now we need to choose loops. Okay, to choose loops, what we do, we start on a wire, any wire. We should not start in an element. It's a wire. Okay, I'm going to go in color here. Let's go with green. For example, I choose here. I start here. And go around the circuit till I get back to that same point. Okay, I'm going to show all the possible loops I can have starting from that point. I can do this. That's one possible loop. And as you notice, it is actually in the clockwise direction. Okay, let me delete that. Okay, now let's start there again, but let's try another loop. Okay, it's the same loop I had earlier, but with the way I drew it, it's in the counterclockwise direction. What I'm trying to say here, the direction you designate the loop does not matter. You do it either way you want. It does not depend on the direction of the current. You choose it any way you want. Okay, so that's the second loop. Okay, let's try another one. I can do this. That's also a loop. All of these are possible loops. Now, the next step says once we choose a loop, I'm going to choose it in the previous screen since we have a lot of stuff written already. So I'm going to go back and I'm going to start here and I'm going to go counterclockwise. In this case, this way. Okay, that's the loop I'm going to choose. And then what they say, write down the voltage drops. Okay. This is essentially saying we need to do the K VR. We need to write down the voltage drops across that loop. So I start at that point. Okay, let me do it with another color. So I started here and I go here till I meet the first change in electrical potential. In this case, the first change is due to a battery. And you notice I meet the minus before the plus. So what I need to write is going to correspond to the change from a low electrical potential, a minus, to a plus. So we are going to have an increase in electrical potential. That's E2, plus E2. And then after that increase, I meet another element in the circuit, a resistor in this case, R2. But I meet the plus in this case, not the minus. So I'm going to go from a plus to a minus. So it's going to be a minus. And the electrical potential change in this case is going to be the electrical potential across the resistor, which is R2I2. So it's minus R2I2. Then after that resistor, going around the loop, I meet the second resistor. But in this case, I'm at the minus one. So I'm going from a minus to a plus. And the voltage change across the resistor is R1I1. So it's going to be plus R1I1. And then I continue. And guess what? I meet a plus. So I meet a plus of a battery. So I go from a plus to a minus. So that's a drop in voltage. That's minus E1. And I'm back at the same place. So I write this as equal to 0. That is Kirchhoff's voltage rule for that loop. Let's try another loop just for exercise. I'm going to choose another color to handle that. I'm going to go for green. Again, first to draw the loop, let me go back to an even other color. So let's go to yellow for the loop. And let's start at this point. And let's go in this direction in this case. So that's my loop, what I have in yellow. And then I'm going to write everything down in green. So starting at this point, the first thing I meet is a plus of a resistor. So I go from a plus to a minus. And the voltage drop across that resistor is R34I3. So it's going to be minus R534I3. And then I meet up with E2, but the minus of E2, so we go with plus E2. And then I'm here, I meet the plus of R2, so we go again with a minus R2I2. And then now I'm here, and I meet with the plus of E3, so it's going to be minus E3. And I'm back where I started, so that's equal to 0. That's another loop rule, or Kirchhoff's voltage rule, KVR. The next step is to write down the node equation or junction equation. Sum of all incoming currents is equal to the sum of all outgoing currents. I'm going back to the circuit again. Notice here, so we need to look for places where we are going to have different currents. Okay, for example, here at this junction, we have I1 coming in this way. We have I3 coming out this way, and I2 coming up. So the sum of incoming is sum of outgoing. In this case, incoming is I1 and I2. Outgoing is only I3. So that's my equation in this case. Another junction I could have used would have been this one. For that junction, I2 is outgoing, I1 is outgoing, and I3 is incoming. So then we get the same equation, I3 is equal to I1 plus I2. So this is writing up the equations. The rest of the problem is going to be just math, and we'll work some examples.